Hi everyone, welcome back to the Reading Club, and in today's episode we'll continue covering this paper, Symmetry in Integer Linear Programming by Francois Margot. This is the second part. If you haven't watched the first part, it's totally fine because the concepts that we are going to see in this video will not be related to the things that we have seen in the first video. Okay, so in particularly this video we will focus on partitioning problem. So let's get into it. Okay, so what exactly is a partitioning problem and why do we care about it so much? So let's try to answer those questions, right? So what exactly is a partitioning problem, right? So we have a set S, right? It has a bunch of elements. Let's use numbers for them, right? So let's call it 1, 2, and up to small s, right? And we want to partition this set into at max t subsets. Okay, so we want to partition it. So this t subsets, or rather at max t subset, should essentially cover all of these elements. So every element has to belong to exactly one of these subsets, and this subset has some additional requirement, right? And that these additional requirements will depend on the problem at hand, right? So this particular structure is very kind of famous in integer programming, and this basically appears in a lot of different theoretical problems. Okay, so some of the examples are bin packing. Let's say bin packing, cutting stock, then there is graph coloring, so either can be vertex or edge coloring, and finally scheduling. Okay, so we are trying to schedule some tasks on bunch of identical machines. Then this problem, it also kind of looks very similar to this kind of partitioning problem. Okay, so of course bin packing, cutting stock, and graph coloring. I'll just describe the formulation of partitioning problem, and it will kind of become clear about why these problems have similar structure to this one. Okay, and particularly why we want to focus on this problem is because this is very symmetric. Okay, and there are ways in which we can break these symmetries in the basic models of this partitioning problem. And of course, if we know some techniques to break symmetries on this problem, then we essentially have ways to reduce symmetries in all of these problems and many other problems that occur in practice. Okay, so that's why we are going to basically focus on this type of problems. Okay, so the basic model that people use for this, it goes as follows. So we have few variables, let's call them x, ij, right? So I will basically represent the index in our set S, right? So we have elements 1, 2 up to S, and j will represent the index in our subsets, right? So that is 1 up to t. We have t possible subsets. So xij is 1 if and only if the item I is in set j, right? So that's how we have, if that is the case in our solution, then this is when this xij variable will take the value 1. Now this basically has symmetries, right? So that symmetry comes from permutations of this set, this t subsets. Okay, so if I have a subset number 5 that has elements, let's just call it 1, 3, and 7, and a subset number 7 that has this element 2 and 8, right? So we can call this one as subset number 7 and this one as subset number 5, right? And this solution is still valid, right? So this new solution, it basically doesn't matter. We can just swap the values of corresponding x variables, xij variables, and this new solution will still remain valid in our original problem, and that's why this problem has a lot of symmetries, right? So in general it can have a lot of other types of variables as well. So let me write down the overall formulation, right? So let's have this x variables, and for that we have objective cx, that transpose x, and let's have some bunch of other variables also, right? So this is plus c, let's call it them y variables, cy, and we have the coefficients for this x plus this coefficient for this y variable, all of them are greater or equal to b, And finally, this is a partitioning problem, so this particular constraint will always be there. So it's called Xij. So every item I, right? So this has to be true for all I, right? So this should be equal to 1 over all j, right? So every item should be placed in exactly one subset j. So if sum over all the j, then Xij should be equal to 1, right? And all of these are binary variable, so they are all 0, 1. Okay, and y can be anything. It can be continuous or integer or whatever. So for now let's call that y's are all integer variables, right? So this is the problem, and we want to try to break symmetries in this problem, right? So we saw these are the symmetries. Now let's discuss what are the different ways in which we can break these symmetries. Okay, so the first technique is called Dantzig Wolfe decomposition, right? So this is very simple technique, which basically says that we are going to formulate this problem completely in a different way. So previously we had Xij variables, where item I is in set j, then Xij will be 1, otherwise it's 0. And this has, if we define the problem like this, then we are basically also adding an ordering of our sets, right? So j represents this ordering of our sets, whereas in the problem we don't have any ordering. So we can formulate another types of variable. Let's call them lambda l, right? So this basically represents a particular set, right? So we have, let's say this set, we have 1, 3, 5. Okay, so this is one set out of all possible subsets. This is one set. And what we want to know is whether this particular subset is selected or not selected. It's either 1 or 0, right? So previously we had item in a subset, whereas now we have presence of a given subset, right? So this can be basically like, you can think of this as a S vector, right? So this vector is basically 1, 0, 1, 0, 1, and all of those other numbers are all zeros. So this is one vector, and there are in total all possible subsets we will look at, right? So there are 2 raised to s possible subsets, 2 raised to s vectors like this, and for all of them we have a unique variable like this lambda l, and for that we will either say whether this particular subset is present or not present. And this is one way of dealing with this kind of symmetries. So now we have removed the implicit ordering of our subsets, but now we have another problem which is called the large number of variables, right? So let's first of all take a look at what happens to the problem statement. So instead of having objectives in terms of x, we'll have objectives in terms of this lambda variables, right? So we have, let's call them C lambda now, C lambda transpose lambda. And the objective for the y variables are not going to change, right? So this is going to be cy y. This is my objective, and the other constraints are also very similar, right? So we had earlier about ax greater than b, so now we will have a lambda plus the y component as it is. All of this is greater or equal to b. Okay, now we need to make sure that every item is selected, right? So let's call another variable z, that is for an item I, and it is corresponding to this set lambda. Let's not call it lambda, let's here let's use this index L. Okay, so this is equal to 1 if this ith item is in lambda L, right? So I want every item to be present in my selected subsets, right? So what we can do is we can just sum over all the subsets, right? So we have ZIL, so we are going to sum over all this lambda L subsets. Let's call them lambda L, right? So this should be equal to 1. Exactly one of this subset which contains this item I should be selected. So that's one constraint, and the other one that we previously did not need was that we need exactly, or rather at max t subsets, right? So we can have this kind of thing, which is sum over all the selected lambdas should be less than equal to t. Okay, so this is something that we previously did not need, but now we need that. Okay, and this all lambdas are binary, z's are binary, y's for whatever they were before, and this basically breaks the symmetry. The only issue is that we have very large number of variables, which is like 2 raised to s, and that's and this problem is essentially too large to fit in memories if we have larger subsets. If s is let's say even 100, just 100 items, we'll have 2 raised to 100 variables. So that's too large for normal computers to fit in. Okay, so how do we solve these problems? We solve these problems using column generation. So this is like a well-known technique where we do not have all lambda vectors present in the beginning. We solve one problem. What we do is basically we solve with some lambda vectors, very small subset of lambda variables, and then we use basically simplex algorithm for that. Right. So this is how we solve the linear program. Right. So we use simplex algorithm. We get the dual cost, and based on those dual costs, we can actually compute the reduced cost of the lambda variables that we haven't actually added in our problem. And if we can basically compute a lambda for which the reduced cost will be negative, and we can just simply add that particular lambda vector to our formulation, and that's the basic idea behind column generation. So essentially we are basically adding inequalities in the dual which are violated. So that's like the equivalent statement we can say for column generation. So this basically column generation, we use it to solve the linear relaxation of this problem, and once we have solved the linear relaxation at the root node, then we have to do branching and everything, and the overall algorithm is called branch and price. So every subproblem will be solved using this kind of column generation, every node, and this overall algorithm is called branch and price, which is kind of very similar to branch and bound, but it has some difficulties because not all variables are present, right? So that's why it's called branch and price. So that's one way of breaking symmetry. So of course I'm not going to go in detail about how branch and price works and how column generation works, but that's the idea behind a way to break this symmetry. Okay, so the second way of breaking symmetries is called partitioning orbitope. Okay, very complicated name, but okay. So what's the idea behind this? So here we are not going to use exponential number of variables. We are going to use the exactly same variables xij. Okay. In fact, let's represent the solution in a matrix. So let's say we have our items on here, and the subsets are here, and this represents my entry of my solution xij bar. So ij. So this entire matrix is my solution. I've just chosen this representation. Okay. Now the symmetry part, it's basically we can basically permute amongst the subset, right? So we can basically permute these columns in any possible way, and whatever this remains it is also a feasible solution, and that's the symmetry. So we want to break that. So how do we break that? We basically assign some value to a column. Okay, let's call it vj. So that is basically sum over all I 2 raised to s minus I xij. Okay, and we say that this matrix, feasible solution matrix, is only feasible if the columns of this matrix are in a non-increasing order, right? So as soon as we have that requirement, the symmetries are broken. Now there are ways in which we can have this requirement modeled as linear constraints, right? So this formulation is based on something called shifted column inequalities. It's complicated formulation, so I'm not really going to explain it, but I'll explain the main idea behind it. So it basically requires picking two subsets, right? So what we need to know is that it requires picking one subset called bar, which is made from picking one I and one j from here, and that results in a bunch of shifted columns, right? So precisely I minus j plus 1, that many different shifted columns, and for all of them, every bar and shifted column we have one inequality, right? So one inequality. So let's represent this inequality as xb minus xs is less than or equal to 0, right? So these are different s that we get from here. So b and s and xb minus xs less than or equal to 0. So clearly this is like one shifted column inequality, and if we add all of this shifted column inequality, then basically we have modeled this requirement, right? So I haven't really defined how B is constructed or SA is constructed. In the paper they have described it. I just think that it's a bit complicated for and kind of not really needed for this video, so I'm going to skip that part. But that's the idea, right? So it basically requires exponential number of constraints in order to model this requirement, and once we do that, then it basically breaks the symmetry. So now we have two ways. In one way we have exponential number of variables, which it's called Dantzig Wolfe decomposition, and the other is that we can formulate this partitioning orbitope by having this exponential number of constraints, and that also breaks the symmetry. Okay, so there is another way of breaking symmetries. It's called by using asymmetric representations. Okay, so what's that? So let's say we have a subset 1, 5, 7. So instead of giving any number to this particular subset, let's represent this subset by picking a representative. So let's say I'm picking 1, then how do I define this subset? I say that 1 is in the same subset as 1, element number 5 is in the same subset as element number 1, and element number 7 is in the same subset as element number 1. Right? So 1 is the representative of 1, 5 and 7. So let's have those variables zij, where I, this is equal to 1 if I is representative of j. Okay, so this is my subset, and there is no particular number that is assigned to this subset. So there is no symmetry with respect, there is no permutations with respect to other subsets, right? So this is represented by a completely different set of variables, right? So this is z22 and z24. So those are the two variables that are 1 here, and here it is z11, 15 and 17 that are 1, and there is no way in which I can swap the values of these variables to get another feasible solution. Okay, so in essence we have basically broken this symmetry. Okay, so there is one still small thing about having this kind of representations, is that we can pick number 5 also to represent this entire set, right? So that's we can pick number 7 also to represent this entire set, and that's that element of symmetry is still there. So we need to still break that, and that is not so hard to break. We can always say that, you know, the smallest element in the subset will be the representative of the subset, right? So we can say that zij is equal to 0 if I is greater than j, right? So for whatever subsets are, the representatives are of the form zii, right? So z11 is a representative, here z22 is a representative, 3 might be also a representative depending on where 3 is in which subset, right? So 4 will be 0, right? So because 4 is represented by 2, so 4 is selected, that's why 4 will be 0. And we can just model this thing by just adding this constraint where zij equal to 1 for all j, right? Sum across all I. So every element has exactly one representative selected, and sum of all the representatives should be less. We should only select at max t representatives, right? So that's a simple thing to add here. So this constraints will is kind of helpful to model this kind of set partitioning problem in a way. So in the paper, they have described a slightly more complex formulation in which they can use asymmetric representations. But I mean, this basically captures the overall idea of this asymmetric representations. Okay, so to conclude, what we discussed in this video was partitioning problem, set partitioning problem, which basically appears in a lot of different problems, right? So bin packing is there, cutting stock is there, graph coloring is there, and some scheduling also is there. In all of this, we see a lot of different symmetries, and this, and in way to break these symmetries, we discussed basically three different algorithms, right? So three different representations. So one of them was formulations. One formulation was Dantzig Wolfe. The second one was partitioning orbitope, right? So this has exponential number of columns. This has exponential number of constraints, right? So of course, like, we don't add all of those constraints at the beginning, we generate them on demand. Here also we don't add all of these columns at the beginning, we generate them using column generation. And the last one was asymmetric representations, right? So this has neither exponential columns nor exponential constraints, but so that's these are like the three different ways of breaking symmetries in this set partitioning problem. And of course, like, this kind of partitioning structure, it actually appears in lot of different practical problems as well, right? So it is the set partitioning is not the only problem, it is around some other problem, it is a part of the problem, and there might be other variables and other constraints along with this set partitioning problem. So in some cases, those symmetries are broken by those other constraints and variables, but in most cases they are not, because this partitioning solutions will represent a symmetric group, and they will always be present, and you can always swap the elements of those groups, swap those permutations, use those permutations, and obtain different feasible solutions for that, right? So all those things we discussed in today's video. Hope you like that. See you in the next video. Bye.